All right, so in this first problem, we have something very similar to what we, in shape at least, as to what we dealt with at the end of our last class meeting, okay? Oh my fucking God. All right, so we have a toroidal coil, or really a toroidal core with a coil wrapped around it. We have an external radius of 7 centimeters and internal radius of 6 centimeters, and the thickness into the page, which would be this dimension right here, is given to be 1 centimeter. We have a total of 250 turns, and there is a flux of 10 microwebers circulating around our toroidal core. The magnetic field intensity in the core is 1,000 amps per meter, and we're asked to determine some things, okay? So let's write down the information. Actually, before we even write down the information that we're given, let's go back and look at our relationships and all of that kind of stuff that we determined from our last class meeting to kind of figure out where things are, right? So we have a toroidal core, or toroidal coil. And so from this, we found that our magnetic flux phi b was equal to N times I times A mu over L, where L is the length or average flux path of the core. So that's our equation for our flux. We also determined the relationship B was equal to mu H, which was mu N I over L. Trying to think of what other types of things we might need here. We know that B is just flux over area. And I think that's a reasonably good. Oh, actually, believe we also learned effectively that Ni is equal to HL. Yep, so that's two different ways to express magnetomotive force, MMF. So I believe that's the bulk of the relationships that we learned or developed in class last, Thursday, okay? So a lot of these relationships are dealing with the average flux path of the core, and that is the first thing that we're asked to find. Several of them are also dealing with the cross-sectional area of the core, so let's go ahead and find that as well while we're at it, okay? So our cross-sectional area A that we're going to be using for some of our calculations is literally just going to be the area of this rectangle right here, right? Because our core has a rectangular cross section, okay? So the width is told to us is simply R2 minus R1. So that's going to be 7 centimeters minus 6 centimeters, excuse me. And our thickness, T, is also given as 1 centimeter. So it looks like our cross-sectional area is just 1 square centimeter. So nothing particularly wild or crazy about that. For our average flux path of the core, so that's part 1, I'm going to call this L sub C. We effectively just need to use our average radius and then multiply that by 2 pi to get the total distance around our circular path, right? So our average radius is just going to be R1 plus R2 over 2, right? And then this is going to be multiplied by a factor of 2 pi. So that would be pi times, yep, so 7 centimeters plus 6 centimeters. So, yep, 13 pi centimeters, or in something we're probably more familiar with, 13 times pi would be 40.8407, so 40.841 and some change centimeters, right? So fairly easy calculation there, nothing particularly wild or crazy. For our second part of our problem, we are asked to determine the magnetic flux density in the core. So what we're looking for is B, okay? So we know that B is simply the flux over A. So gosh, isn't it handy that we already calculated A and our flux was given to us, right? So B is phi B over A. So that's going to be 10 microwebers. So let me just go ahead and write that out. So that's 10 times 10 to the minus 6 Webers divided by 1 centimeter squared. Now, we are expecting the units of our magnetic flux density B to be in Tesla, where a Tesla is a Weber per meter squared. So we're going to have to convert our centimeters into meters to make this stuff work out, right? So let's just go ahead and do that real quick. So there are 100 centimeters per meter, and we need to square that conversion factor. So this to me looks like 10 times 10 to the minus 6 times 10 to the 2 times 10 to the 2. So let's just put that as 10 to the 4 over 1 meters squared. So that would be 10 times 10 to the minus 2, or 0.01 Webers, excuse me, per meter squared, or 0.01. Did I? Yeah, it should be 0.1. I have that extra 10 there, my bad. 0.1 Webers per meter squared, or 0.1 Tesla. So nothing particularly crazy there. Let's see, the next thing we're asked to calculate is the MMF. So that's for part C. So you'll see in some textbooks that MMF is given, I don't even know if I can draw it, by some fancy script F that I can't draw for shit. So I literally usually just say MMF for magnetomotive force. And we have two different things, right? We have a relationship for N times I is our MMF, and we have H times L, our flux path. Well, which one of those can we apply based on the information that we're given? So let's start there. Are we given a current?
Well, no, well, we are given N.
We are given N, but we aren't given I, so that's two unknown quantities. So the other one would be H times L. Well, we calculated L in part A. What's this 1,000 amps per meter right here? This is our magnetic field intensity, which is H, right? So solving for I is actually part D. So this is going to be H times L. So that is 1,000 amps per meter times 40.841 centimeters. And then while I'm at it, 1 meter is 100 centimeters. So getting rid of those things. And this apparently comes out to be 408.407 amp turns. So that's our typical unit for MMF, and it comes from actually this definition right here, where N is measured in turns and current I is measured in amps. But even when we have it as H times L, we'll still consider the units of MMF to be in amp turns. Okay. And then lastly, we have calculating our current. So now that we know our MMF, we can simply divide by the number of turns. So current is going to be MMF over N. So that's 408.407 amp turns over 250 turns, gives us 1.634 amps of DC current flowing in our coil in order to generate that 10 microwebers of flux. Okay. So in-class assignment 1, done. Turn it in digitally before the beginning of next class meeting. All right. Sorry I went through that quickly, but I started class 10 minutes late because of technical difficulties, and we've got shit to do. Okay, so at the end of our last class meeting, let's call this magnetic circuits. So at the end of our last class meeting, we effectively stumbled onto a relationship, right? So we had a toroidal coil, or what we learned is for a toroidal coil, our magnetic flux, phi B, was equal to Ni times A mu over L. And I rearranged this thing and expressed it as Ni is equal to phi B times L over A mu. And I believe I mentioned that this is effectively our Ohm's law for magnetic circuits, right? So this is of the same form as V is equal to I times R, where our MMF is playing the role of V, our flux is playing the role of current, and this thing right here, which we're going to call reluctance, excuse me, is playing the role of resistance, okay? So reluctance, I don't know why I can't spell it for shit today, is a measure of how difficult it is to pass magnetic flux through a particular path. So it is similar to resistance in as much as resistance is a measure of how difficult it is to pass current through a particular path. And so that's why it's effectively playing the role of resistance in what we're going to call a magnetic circuit, okay? So essentially a high reluctance means that it is more difficult to pass magnetic flux through a particular path, which in turn means that it is more difficult to magnetize that path, okay? So for some applications, we want things to have very low reluctances because we want to be able to magnetize things very easily, okay? So if we consider an industrial transformer or something like that, where we want it to work very efficiently and we don't want to have to put in any extra energy to do anything to cause that conversion of voltages and currents and all of that kind of stuff, typically speaking, we are going to want a relatively low reluctance core. And we can see that our reluctance is inversely proportional to our permeability mu, right? So we want something with a really, really high mu value because that means that we can magnetize it easily and we'll have low levels of losses and all of that kind of stuff. For other applications, though, we might want to have a high reluctance, okay? And we're going to talk about this a little bit later on, but one of the best and easiest ways to introduce a high reluctance is to introduce air gaps into our magnetic circuits. Because if we have air, it's not ferromagnetic iron, steel, cobalt, or whatever. It's going to have a lower value of mu, and that's going to cause the reluctance to go way up. Okay. So what a high reluctance medium allows us to do is effectively store more energy. Okay. So when we're designing things like inductors and all of that kind of stuff, air gaps are typically good. For transformers, air gaps aren't typically good. And then for rotating electric machinery, we don't have a choice but to have an air gap because we have something spinning inside of something else. If they were connected to each other, the whole damn thing would spin and it wouldn't work right. Okay. So we're going to see the full gamut of reluctances as we look at about different equipment in this class. Okay. All right. So we came up with this relationship for a toroidal coil, but I have expressed it in such a way that it's only dependent on the average flux path, meaning that we could really apply this to any shape that we're interested in, as long as it has a well-defined cross-sectional area, the material has a known permeability mu, and we can calculate the path that the flux is going to take, okay? So let's look at something that's probably more commonly seen, at least in transformers and all of that kind of good stuff, where instead of having a toroidal coil, we have like a squarish shape, okay? So let's consider the following system. So I think I drew my core in blue last class, so I'll continue to try to remember to do that. So let's say that we have something like this. So we have a rectangular core, right? Still forming some closed system. And we are going to wrap a wire around it, like so. Where I'm going to assume current is flowing in the top part of the winding and it's flowing out the bottom part of the winding. And we're going to say that this coil has N turns, okay? So I'm going to define some dimensions for this particular thing. I'm going to do those in green. So let's say that this is the length of our core material. So I'm going to call this L1, bless you. This dimension will be the thickness of our core material. This will be a second length, so let's call this L2. And then we have some uniform width. So let's call this W, and this dimension is also the exact same width. So I believe I have identified this as all of the dimensions that are necessary for this particular core shape and coil.
What's that length in the bottom right?
T, the thickness or the depth of the material into or out of the page, right? Okay, so if we were to approach this as a magnetic circuit, we are effectively going to construct a schematic diagram representing this physical system, okay? So our coil is our MMF source, and it's playing the role of a voltage source. So I'm literally going to write my coil as if it were a voltage source, okay? So we might have something, I'll just do it over here to the right. So something like this, where I'm going to have N times I, okay? Now, this section of my core material here, this leftmost leg, will have some reluctance. So I'm going to choose to put a reluctance that I'm going to call R left. And I'm going to try to do this as a fancy looking R. And that represents the reluctance of the left leg of our core. Then I've got the top leg of our core. So I'm going to have R top. Then the right hand leg, R right. And lastly, the bottommost leg of our core, which will be R bottom. And that is my magnetic equivalent circuit for this physical system, okay? And then I'm going to just denote here that my expectation is that I will consider positive flux. Let me use a different color. I think was using purple for flux lines the other day. So it might have been light blue. I'm gonna use purple today. No, shit. I use purple for the average flux path. I'll use that light blue. So this is what my assumed direction for my flux around this magnetic circuit is, where I'm just assuming correctly that the flux is going to be leaving the positive polarity terminal of my MMF source. And for what it's worth, if I wrapped my fingers in the direction that the coil is wound and use my thumb, it would be pushing the flux around that clockwise path, okay? So this magnetic circuit agrees with everything that we've learned to this point. Okay? So if we wanted to figure out the flux flowing around our circuit, for instance, or the amount of MMF required to push some amount of flux around our circuit, things like that, we would need to know what the reluctance of this core is, okay? So let's go ahead and see if we can figure out what REQ is going to be, okay? So let's say that our equivalent flux is just going to be R left plus R top plus R right plus R bottom. And so how would we find these various reluctances, okay? So let's start with the left-hand side, right? So R left, okay? So if we look back up here, our reluctance is simply the length of our average flux path divided by our cross-sectional area times mu. That's what it's going to be 100% of the time, okay? So let's try to define what our average flux path here might look like, okay? So I think it's going to flow effectively in the middle, which is exactly how we treated it for our toroid, okay? So we've got some average flux length of the left-hand leg. We've got some average flux length on the top, some average flux length on the right-hand leg, and some average flux length on the bottom, like so. So how would we quantify this average flux length for just the left-hand leg in terms of the dimensions that we were given? So I don't think it's L2 because it's shorter than that, right? If it were L2, the flux would be traveling from the bottom all the way to the top before it changes directions. L2 minus the width, right? Because we have half the width on the bottom side that we're not traveling through and half the width on the top side, okay? So L2 minus the width, all right? And then we're gonna have mu, which is a material constant. I haven't given it to you, so I'm just gonna leave it as mu. And then I have my cross-sectional area, okay? So what's my cross-sectional area?
T times W.
So T times W, absolutely right. So let me try to draw a little picture here so that we can see it, right? So my cross-sectional area that my flux is traveling through is going to be this thing right here. And that is definitely has a width of W and a depth of T. So T times W, 100% correct. Okay. So if we had values for those particular parameters, that would allow us to calculate our average flux path for the left-hand leg. Now we can look at this damn thing, I believe, and see that the right leg of this core has the exact same geometric properties and all of that kind of good stuff. And it's the same material. Our core didn't magically change materials in the middle of it or anything like that, which we can do, but we didn't do here. So I think that this is going to be the exact same thing as R right as well. Okay. So now let's figure out what's going on for the top. Okay. And then by looking at the thing, we should be able to see that the reluctance of the top portion of the core is going to be the same as the bottom because once again, they have the same cross-sectional area, the same length, width, and thickness. Okay. So, excuse me. What is the length of the flux path for the top section and bottom section? L1 minus W yet again, because it's not going all the way across the entire length. We're losing half a W on the left-hand side and half a W on the right-hand side.
The bottom. U times. W squared.
So let's look at the cross-sectional area there, okay? So we have this dimension, which is given as the width, and then we have this dimension right here, which is still the thickness T. So it's still just going to be WT.
The only thing that changed was.
Exactly right. So I chose to write this one as W times T instead of T times W. It's the same thing, doesn't particularly matter, right? And we can see very easily by inspection that the reluctance of the bottom is the same as the reluctance of the top. And so REQ is just going to be twice R left plus twice R top. But we can actually notice something different or something else here as well if we were paying enough attention, okay? So what I mean by that specifically, and this will not be true for all cases, but it'll be true for a lot of them, the cross-sectional area of our core never changed, right? So realistically, we could have just done the length of the average flux path as one big thing, and then the cross-sectional area as that one computation, right? So this is actually going to be the same thing as simply twice L1 minus W plus twice L2 minus W all over mu WT for this particular case, where since our area, our cross-sectional area didn't change, we could have just used the average lengths of the flux path like we did for our toroidal coil and calculated the equivalent reluctance in one go, right? Just by adding those lengths together. Okay. All right, so we could further play around with this guy, right? Just for what it's worth. So I have a 2 times L1 and a 2 times L2, so I could write that as 2 times L1 plus L2. And then I have a minus 2W and another minus 2W, so this would just be minus 4W all over mu WT, like so. Just
And then can we get rid of the W?
we cannot, because there's no W term over here, right? So algebra won't let us, or it would look like 2 times L1 plus L2 over W minus 4 over mu T, which isn't really getting rid of the W, it's just moving it. So it doesn't really help it. So just for the sake of argument for this particular shape, let's say we wanted to know what our flux is. Okay, so let's say that we knew the number of turns and we knew the amount of current flowing through our coil as I, then our flux would just be Ni divided by our equivalent reluctance, or Ni times mu Wt over twice L1 plus L2 minus 4W. And that's good enough to go. If we wanted to know H, for example, that would just be Ni over our average flux path. So that would be Ni divided by twice L1 plus L2, sorry. Minus 4W. B, our flux density, would be mu times H. So that's just going to be mu Ni over twice L1 plus L2 minus 4W, or B is given by flux over area, right? So if we look at our flux relationship and we divide by area, well, area is just this WT, right? So if we get rid of that, we still just get mu Ni over twice L1 plus L2 minus 4W for this thing. So all of our relationships, and it doesn't matter in which way, shape, or form we reorganize them, we're going to wind up getting the exact same results, right? So if we know the reluctance, we can, within a couple of steps, figure out anything else just given or dependent on what pieces of information we're given. So let's look at the second in-class assignment real quick. I'm trying to remember exactly what these are. I might change my mind in a moment. Problem 2 has got an air gap. We're not quite ready for that one yet. Let me just. Yeah, this is a legit one. Okay. So we've got this thing, right? We've got a core. It has a uniform width of 14 centimeters along 3 of the legs, and then the width is only 5 centimeters for the 4th leg. Okay. The depth of the core into the page is 10 centimeters. So if I tried to draw this thing out a little bit further, just for illustrative purposes, this thickness here is T. Okay. We're told that our core permeability is 2,000 times the permeability of free space, and our coil has N equals to 300 turns. Okay. So our goal here for part A is to determine the current needed to produce a specific magnetic flux of phi B is equal to 1.25 Webers. So let's look back at things just really quickly here. So our goal is to figure out flux. Well, we've got an equation for flux right here. Thank you. Ni over our equivalent reluctance. And that to me is probably the easiest way to do this. So the first thing we're going to have to figure out is our equivalent reluctance for this particular ship. Okay. So I'm just going to make a note here for part A. Flux is N, which is given to us. I over REQ, and we're trying to find I for a particular flux. So we would rearrange that and say that I is phi times REQ over M. Does that make sense, everybody? Just simple algebraic manipulation of one of the expressions that we've been using. Okay, so phi B is given, N is given, so all we've got to figure out for part A is the equivalent reluctance. So, anybody have any thoughts?
Just use that formula that we just had for our equivalent. No.
So we can't quite use that because our cross-sectional area isn't constant around the whole thing, right? So if we looked at our cross-sectional area, and let me try to draw this out here, right? So if we looked at just this part right here, I think I was doing it in pink. So this would be 14 centimeters times our thickness, which is 10 centimeters. So that's our cross-sectional area for that particular leg. If we look up here, we have 14 centimeters times 10 centimeters. So that's pretty good, except for that rightmost leg. Absolutely right. So this one is 14 centimeters times 10 centimeters. But this guy over here kind of messes things up a little bit. Okay. So this guy is just 5 centimeters times 10 centimeters. Let me move that 10 centimeters over so we can see that dimension. Okay. So I think that we could actually just break this thing up, exploiting the fact that 3 of our sides have the same cross-sectional area by finding the flux path through the length of the flux path through those 3 legs, finding that equivalent finding that reluctance, and then finding the reluctance of the right-hand leg and just do it in 2 instead of breaking it up into 4 because the geometry makes it a little bit easier. Okay. So I'm going to do the flux path 1 in this color, right? So I'm just going to have a kind of guesstimate here. So let's say that it starts right here, goes all the way across like so, down like so, all the way across like so. And this total length, we're going to call L1. And then I'll do the other flux path length in a slightly different color. Hopefully this looks different enough on the screen. Can you tell the difference between that light purple and the darker purple, or should I use something else?
I can tell.
Okay. And let's call that guy L2. Okay. So let's start with L2 because I feel like it's probably the easiest one to figure out. So what do you guys think that one should be? The length of the flux path through the right leg.
Um, 18 centimeters, I guess 16 centimeters minus 14.
Okay, so where you got 60 centimeters from taking this whole length from here to here, right? Okay, I would agree with that. I would have done it in a slightly different way, but it would have got the exact same result. So we know that from here to here is 32. Then we add 7 more because we have half of this 14 and 7 more up here. So it's just 32 plus 14 effectively, okay? So 32 plus 14 is 46, if my mental math is correct. Tell me if it's wrong. All right, so L2 is 46 centimeters. Are we all okay with that? We understood where it came from. Okay. L1 is going to be a little bit more difficult. So I think we can all agree that this portion of the left flux path is the same, right? Exact same length as what we had as L2. So I'm going to put 46 centimeters, and that's taking care of the vertical bit through that leftmost leg. And now we're just going to have whatever is going through that top portion twice because the top and the bottom has the same cross-sectional area. So what's the length of just the top part of the flux path?
That would be 32 centimeters plus 2.5 plus 7.
Yep. So 32 plus 7 is 39, plus another 2.5 is 41.5. All right. And I will not embarrass myself by getting this wrong doing it in my head, so I'm gonna put it in my calculator. 46 plus twice times 80,
85 plus 46.
83 plus 46.
You embarrassed yourself. Oh, I don't know. I wrote down 42. Down 42, okay? I'm sorry. I wrote down 42.
All right, so we've got our lengths. So now we can find REQ fairly straightforward, right? So REQ is just going to be our length L1 over mu times our area. I'm just going to write that as mu A and we'll plug stuff in, plus L2 over, I'm going to call that A1, and then mu times A2. And now let's just throw some numbers in this, right? So L1 was 129 centimeters. Mu was 2000 mu naught, if I'm remembering correctly. Yep. So that's going to be 2000 times 4 pi times 10 to the minus 9 henries per centimeter. So let's write it down as henries per centimeter right now, and we'll play around with the units here in a moment when we need to. And then our cross-sectional area for this section, so this is what's A1 is, and this guy over here is A2, is just 10 centimeters times 14 centimeters. And then we've got the right-hand leg, which has a total flux path length of 46 centimeters. And then once again, 2000 times mu naught, so that's 4 pi times 10 to the minus 9 henries per centimeter times 5 centimeters times 10 centimeters. And we should be able to throw this into our calculator. So I'm going to find the reluctance of each of these legs just so that I don't overwhelm my calculator. So 129 over 2000 times 4 pi times 10 to the minus 9 times 10 times 14. And so that gives me 36,662.4779. So let's call that 478. Let's look at our dimensions here really quickly. Okay. Because we haven't really talked about the units for reluctance, so we'll get around to that in just a second, okay? So I have a centimeter here in the numerator that's going to cancel a centimeter here in the denominator. Are we all okay with that? Okay. Then I have a per centimeter that's being multiplied by centimeters. So those guys cancel each other out. So it's looking like I'm going to have units of per Henry, okay, which isn't wrong, but this is another one of those weird cases where we call it something else, even though it's dimensionally the exact same thing as 1 over a Henry. So just as a quick aside, you guys may recall from the 280 course that 1 Henry is equal to 1 volt second per ampere, right? Well, we learned in class on Thursday that a volt second is just another word for a Weber, okay? So that would be a Weber per amp. So the inverse of this is what we're going to call amp turns per Weber. And that's our traditional unit for reluctance. I personally feel like calling it inverse of Henry's would have been easier, but for whatever reason, for the last 140 years, they've been calling it amp turns per Weber, so that's what I'm sticking with. Okay. Yeah. Yeah. So 36,662.478 amp turns per Weber. Now, I know that you guys don't actually have any frame of reference for this, but this is not a particularly large reluctance, okay? So the amps comes from the fact that we have 1 over amps and we're flipping that over. The turns, the best explanation that I can give you is we've got a coil that's supplying our thing. So it's just the units that typically wind up getting used. I don't really have a better explanation as to why turns got tacked on there than that's what's traditional, and turns is a dimensionless quantity because it's just literally counting the number of turns. So including it or excluding it really doesn't impact the units from a dimensional aspect in any way, shape, or form. So amp turns per Weber, for whatever asinine reason, is the conventional unit of reluctance that we're going to use. All right, so throwing in the other side of this thing, we've got 46 divided by 2000 times 4 pi times 10 to the minus 9, and then 10 times 5. And so this comes out to be 36,605.6369. So let's call this 637, and it'll have the exact same units. So once again, amp turns per Weber. So I want you guys to notice that the right-hand leg has almost the same reluctance as the rest of the magnetic circuit, and it's because its cross-sectional area is so much smaller, right? So if we restrict the flux to flow in a smaller area, we see higher values for reluctance. All right, what the fuck just happened?
No.
Damn it.
They do not want us to learn one of this at all. Yes, they got it.
Well, I'm very
I'm
That's a skill shit, it's a skill issue.
It's a major skill issue. Of course I am. Well, you know it's gonna be tagged.
And then you got like busy.
That's why I'm gonna order it. Look for parking for 30 minutes, and by the time I find parking, it'll be ready.
So it was yesterday, or yeah, I was like, don't you want to just walk over?
Uh-oh.
Hooray! Darn.
Messed up with one of these ports somewhere. What's happening? All right, let's continue before the projector and or whatever takes another shit. All right, so we've got our equivalent reluctance. Made a simple observation here to see how impactful cross-sectional area is for this particular thing. So let's get back around to solving for our current, right? So the equation that we have developed, just rearranging other things that we have derived, is that our current is equal to flux times reluctance over our number of turns. So in that case, our current I is going to be our flux of 1.25 Webers times our reluctance. So I should probably add those two things together really quickly. So 36,662.478 plus 36,605.637 comes out to be 73,268.115 amp turns per Weber. And then we divide by N, which is 300 turns. And notice now that Webers cancels Webers, turns cancels turns, and we're left with amps, which I think is probably the best explanation for why the hell the units of reluctance are amp turns per Weber. And so this winds up being 305.284 amperes. It is. Exactly right. Yep. Pretty much, yeah. Or using like the units of radians or whatever for an angle, it's a dimensionless quantity. All right, so we figured out the amount of current required to sustain a flux of 10 microwebers in this particular, excuse me, not 10 microwebers, 1.25 Webers in this core. So that's a pretty large value of the flux, which is why it took a whole hell of a lot of current to get there, okay? Now we need to find the magnetic flux density for at the top of the core. And so by that, I mean the flux density traveling through this section. So how would we do that? Exactly right. So for part B, our magnetic flux density B is simply flux over cross-sectional area. So perfectly correct, right? So our flux was 1.25 Webers. Area. 1.25 Webers. Our area in this case is 10 centimeters times 14 centimeters. And while we're at it, because we know that Tesla, the unit of magnetic flux density, is Webers per meter squared, we'll go ahead and throw on a conversion of 100 centimeters per meter, and then we'll square this guy. So 1.25 times 100 squared divided by 10 times 14 gives me 89.286 Webers per meter squared, which is a Tesla.
You do have that too. So then define the right side, we do the exact same thing.
Except we would use the cross-sectional area.
And so.
Mhm. Yep, absolutely right. So for part C, exact same relationship. B is going to be phi B over A, but now we use the area of the rightmost leg of our core. That would be 1.25 Weber over 10 centimeter times 5 centimeter times 100 centimeters per meter quantity squared. And that comes out to be 250 Tesla, which is a ridiculously strong magnetic field, but we put 300 amps of current through something that seems okay. All right, and then lastly, we want to effectively do the inverse. If we bump our coil current up to 500 amps, what will our flux be?
Oh. Oh. So you see that.
So for part D here, we're just going to use this relationship, right? Because we know the number of turns, we know the current, we know the equivalent reluctance. We're trying to solve for flux, okay? So phi B is Ni over Req. So 300 turns times 500 amps if the coil current is changed to 500 amps,
Oh, okay. Yeah.
divided by our reluctance of 73,268.115 amp turns per Weber. And then notice that we have turns cancels turn, amps cancels amps. So we have 1 over Weber, which is the same thing as Weber, the unit of flux. And so throwing this into our calculator should come out to be 2.047 Weber. Okay, so that one was a fairly straightforward example. Let's look at a shape a little bit different, okay? Actually, before I tab out of that, are we all okay with that guy? Okay. So let's look at a different core shape. And this is another one that's pretty commonly used, okay? Especially for transformers and things like that. So let's say that we have a shape that looks something akin to this. And I'm going to go ahead and define some dimensions and all of that kind of good stuff. So this total length down here is going to be L1. This will be our thickness. Yeah, effectively. Here's what we're going to call L2. We're going to assume that this width up top is W1. Same thing on the bottom. Sorry, I forgot to draw part of my thing, or maybe I accidentally erased it. Bless you. This width right here, I'll call it W2. Like so. And let's say that we put a coil on that middlemost leg. So current's flowing this way, returning this way, and it has n number of turns. So if we had placed two coils on that middle leg, this would be what's commonly referred to as a shell type transformer, which is a very common transformer architecture for low power applications. So if you were to crack open a power supply or anything like that in your home kind of thing, like for your computer, this is the type of transformer that it would have. Okay. But this isn't a transformer. This is just a oddly shaped inductor at this point because it's only got one coil on it. Anyway, so let's, apply some math at this thing. Let's say that L1 is 80 centimeters. L2 is 50 centimeters. W1 is 10 centimeters. W2 is 8 centimeters. T is 10 centimeters. And for what it's worth, mu is 5,000 mu naught. Okay? And what I want us to try to find is the flux flowing through the left leg of this guy if n is equal to, let's make it 100, and I is equal to 10 amps. Okay. So the reason why I've chosen to ask us to find phi b for just the left leg is because I want us to see that we can literally treat this thing like it was a circuit and use circuit analysis techniques to determine things that won't involve a whole bunch of extra steps if we're smart about things. Okay. So what I am suggesting is that if we were to find, let's call it this flux, which I'm just going to call phi total. So that's the flux that's being, total amount of flux being generated by our coil. We could use flux division, which is the exact same thing as current division in a conventional electrical circuit, to find the flux that goes off to the left without having to do a whole bunch of extra math. Now, realistically, we could effectively apply Gauss's law for magnetism, which says that the total amount of magnetic flux density entering and exiting a closed surface has to be equal to zero, because that's the same thing as Kirchhoff's current law for an electric circuit, right? So we could use that if we wanted to, but this idea of flux division or current division will actually make things a little bit easier to do. All right, so how would we go about finding phi total? Let's start there.
Well, you probably find E first.
So we would find phi total first because it's the thing that's dividing and producing the flux that's just flowing through the left leg, right? So I would argue that phi total is just going to be Ni over the equivalent reluctance seen by the coil, right? So just let me double check because I'm seeing some questioning looks. So let me make sure I haven't done the wrong thing. No, it looks like the equation is Ni over Req. So why couldn't we use that, right? So if we find the total flux in the system, once we know that, we should be able to figure out how much flux is carried by any individual leg of this thing, okay? So let me draw an electrical circuit representation of this thing because this one is a little bit more complicated, so we'll have to sort some stuff out, right? So if I put my MMF source here in the middle, I'm going to call this R mid. This is just Ni. And then I have what I'm going to call R left over here. And R right over here, where left constitutes, let me this bit, and this bit. So I'm going to put a note here. This is L left. This bit, and this bit is the right path in total. We'll have to play around with that in a moment. And then just for the sake of argument, I'll do bright green down here. This bright green length is L middle. So I'm trying to eliminate, breaking that left flux path and that right flux path into 3 smaller flux paths. Now, this might bite me in the ass a little bit because I know that my cross-sectional areas are different, but we can sort that part out, okay? So, based on how I'm looking at this particular magnetic circuit, does that electrical equivalent circuit make sense? Let's start there. Anything that anybody's not catching? Okay, so the easiest part of this thing is probably going to be the middle. So let's go ahead and sort that out real quick. So what should the reluctance of my middle path be? Well, it's just the length of the flux path divided by mu times the cross-sectional area, right? So what should my length be here? L2 minus W1. Because W2 is the horizontal dimension of the vertical legs. W1 is the vertical dimension of the horizontal leg. So I think it should be L2 minus W1. So that's 50 minus 10 is 40 centimeters. So I'm going to write it down as L2 minus W1 over mu C, which is just going to be my core permeability. What would my cross-sectional area be for this guy? W2 times T. Absolutely right. So that would be 40 centimeters over, what did I do? 5,000. 4 pi times 10 to the minus 9 henries per centimeter. W2 was 8 centimeters. T was 10 centimeters. And this is something that I can throw in my calculator, and I believe it comes out to be 7.958 times 10 to the 3 amp turns per Weber, according to my prior notes. Are we okay with that? All right. So now let's talk about the left-hand side. Okay. So we've got this section on the top, and we've got a section on the bottom. Those have the same length and they have the same cross-sectional area, so we can lump those together pretty easily, right? So I'm going to do twice. So what's the length of that top portion of the purple path? So let's assume that that middle bit is exactly halfway in between.
1/2 L1 minus 72.
So 1/2 of L1 minus a W2. Nope. I think it should be. No, you are right. Minus half of a W2. Yep. So all the way from here to here is half of L1, and then we would subtract half of W2. So 1/2 of L1 minus 1/2 of W2. Okay, I'm on board with that. And then we would have mu C. What is our cross-sectional area for that portion? W1 times the thickness T. Okay. Yes. Okay, sure. So let me extend some things here, right? So we're looking from the middle of this thing all the way out to here. So this full length right here is 1/2 L1. Are you okay with that? Okay. Then I also have to take away this little bit right here that I've indicated in red. That is 1/2 of W2. Okay. The reason why I've multiplied that whole thing by 2 is because I have this path right here and this path down here of equal lengths. So I'm just adding those two guys together. So that's where the 2 out front came from. Caleb, how may I help you? I could, because the 2's and the halves cancel out. Absolutely.
Yeah.
Yep.
That's what I was thinking.
I absolutely could do that for sure. And we'll probably wind up doing that when I calculate it, because that's less bullshit to put in my calculator. Yes.
I was just making sure that I wasn't
Nope.
thinking it.
Seems like a perfectly reasonable thing to do. Okay. So we've got the topmost path, part of the path, and the bottommost part of the path taken care of. Now we need to get that vertical path. Well, I think that vertical path has the exact same reluctance as the middle leg, because it has the same dimensions and the same cross-sectional area. So I'm going to be lazy, and I'm just going to put plus R mid. Okay. And I'm going to be extra lazy and say that this left path has the exact same reluctance as the right path, because they have the same dimensions and all of that kind of good stuff. Okay. So L1 minus W2 is going to be 80 minus 8. So that is 72 centimeters over 5,000 times 4 pi times 10 to the minus 9 henries per centimeter times, let's see, my cross-sectional area here was W1, which is 10 centimeters, times T, which is 10 centimeters. And I'm going to add to this thing that 7.958 times 10 to the 3 amp turns per Weber. So let me throw this into my calculator real quick. So 72 over 5,000 times 4 pi times 10 to the minus 9 times 100. Divide that by 10 to the 3. So 11.459 times 10 to the 3 plus 7.958 times 10 to the 3. So I get a total of 19.417 times 10 to the 3 amp turns per Weber. So from there, that's the same thing as R right. So what would the equivalent reluctance be as seen by our coil? Don't give me a number yet. How did you come up with that? So I have an issue. 2R left implies that the left branch and the right branch are in series, but I don't think they're in series. They are in parallel, my dude. So I think it should be R mid plus half of R left, right? Because R left in parallel with R right when they're equal to each other is going to be just half, right? So REQ just to prove that really quickly. So what Anna is suggesting, this is a quick aside. So let's say that I have a resistor R1 in parallel with a resistor R2, like so, right? I believe, all know that REQ should be 1 over R1 plus 1 over R2. And I think you guys should know that that's the same as R1 times R2 over R1 plus R2, right? If those are equal to each other, so then that's going to look like R1 squared over twice R1 is just 1/2 times R1. So whenever we have two identical things in parallel, we just cut it in half.
That's my favorite one.
Yep.
So,
Get rid of all this bullshit. It really wants to stay. It's pissing me off. I mean, maybe it might have something to do with the fact that I reset this computer once every 3 months, so I might have to do that after class today. I just get out of class, close it up, throw it in my bag, and open it up for the next class. And yeah. All right. Well, something to add to my to-do list for today. Okay. So multiply that by 0.5, add 7.958. So I get an REQ of 17.6665. So let's call that 667 times 10 to the 3 amp turns per Weber. So phi total should just be Ni divided by my equivalent reluctance. So N was 100 turns 10 amps over 17.667 times 10 to the 3 amp turns per Weber. So 1,000 divided by 17.667 times 10 to the 3 gives me 0.0566, so 0.57 Weber, or 56.603 milliweber. Okay. So what's phi b, which is the flux through the left path, going to be? We should be able to look at this and tell. Exactly right, because it's going to divide evenly between those two identical flux paths. Absolutely right. So phi b is just 1/2 phi total or 28.301 and some change milliwebers, right? So we can intuitively see that our understanding of current division works here just like it would for flux division, because these two paths are identical to each other. But if they weren't identical to each other, we could still just use the ratio of the reluctances and all of that kind of good stuff like we did in circuits 1 or power 1 or whatever the hell you want, whatever last class you guys had with me. My brain is so fried at this point. But we can use those exact same principles to figure out how the flux is going to behave, because it behaves identically to the current. We could also use effectively MMF division in place of voltage division for things like that as well. So all of our basic circuit analysis techniques that we've learned in our previous classes can be applied to magnetic circuits, as long as we remember that everywhere that we had a voltage in an electrical circuit, that's what our MMF is. Everywhere we had a current in an electrical circuit, that's what we are now considering flux. And everywhere we had a resistance, we now have a reluctance. All right, so we only have 12 minutes left of class, and that is not enough time for me to get into air gaps in magnetic circuits. So we're going to leave problem 2 from this in-class assignment for next class after we talk about air gaps and all of that kind of good stuff. So within 2 days, I am already half a class behind. This is amazing.